Okay, here we have a more complicated trigonometry problem. ABC, ABC and ACD are right-angled triangles. Find AC. Now AC is one letter to another letter, A to C, so that means find the length of AC. Now unknown lengths, if I haven't used X already, I'm going to call it X. Okay, now to find AC, that is in the triangle ABC, and I know the other two sides, so I'm going to draw the triangle ABC like this. So I'm drawing a new diagram just involving the triangle ABC. Okay, now there I have a right-angled triangle, and I've got all three sides labelled, 2 with distances and the third there. No mention of any angles at all in that. Now, it's very easy in maths to think that you've always got to use the last bit of maths that you've learnt to solve a problem. But you can only really show you've mastered your mathematics when you can apply all the mathematics you know appropriately to a situation. Now, this is a question that all of you could have solved before you learnt trigonometry at all. Have a little think about what bit of mathematics I could use here. Yeah, that's right. It's a right-angled triangle. I know two sides. I don't know the third. Pythagoras' theorem. And Pythagoras' theorem says, in a right-angled triangle, a squared plus b squared equals c squared, where c is the hypotenuse. In this triangle, x is the hypotenuse. So we've got, in these two, we can call A and B. So we've got 14.5 squared plus 4.6 squared equals the hypotenuse squared, x squared. So that tells me that x squared is equal to 14.5 squared plus 4.6 squared. So x squared is 231.41, and to find x I find the square root of that. So square root answer equals, we get 15.21 centimetres. Okay. Now it says find the angle CAD. Well, that's in the triangle ACD. So I'm going to draw the triangle ACD. I'm going to draw it here as the right angle. Now AC I now know is 15.21. CD is 5.4. And I need to find the angle ACD. So this is one of these three-letter codes for describing an angle. So let's write ACD on there. So we need to find the angle CAD. So C to A to D. So that has made that angle there. And we'll call that angle theta, because we haven't used theta elsewhere in the question. So that is our angle. 5.4 is opposite the angle, and 15.21 touches the angle but is not the hypotenuse, so that makes it the adjacent. So I've got opposite and adjacent, so tan theta equals opposite over adjacent. Tan theta equals opposite 5.4 over 15.21. So I know the ratio. I want to find the angle, so I have to use the inverse tan function, tan minus 1 of 5.4 over 15.21. And on my natural display calculator, I can enter exactly that. To get inverse tan, I do shift tan, press the fraction button, 5.4 arrow down, 15.21, arrow out of there, close the brackets, equals, checking the calculator is set on degrees, and I get 19.54 degrees. So to one decimal place, that is 19.5 degrees. Okay, so that is an example of a two-step trigonometry problem, where in the first step we actually had to use Pythagoras' theorem, which is still part of trigonometry. It's to do with triangles, it's to do with working out missing sides in triangles. So that's how to do that one. Now let's have a look at another one of these two-step problems. Let's just tape this down here. JKL and JLM are right-angled triangles. JKL, that's that one right-angled triangle, and JLM, that's that right-angled triangle. Find the side JL. Okay, unknown side, I'm going to label it X on there, and again, I'm just going to work out this triangle here. So I'm just going to draw this triangle here, 20 degrees. You may consider it a bit of too much effort to draw another triangle, but I promise you, if you draw your triangle separately, you're far, far more likely to get the triangle correct. So there's my rather little triangle, but it will do. Let's label those JK now. So X is across the triangle opposite the right angle, so that's the hypotenuse, and 8 touches the angle, so is the adjacent. Adjacent and hypotenuse, I'm going to use cos theta equals adjacent over hypotenuse. Substituting in, my angle is 20 degrees, cos of 20 degrees equals the adjacent, which is 8, over the hypotenuse, which is x. Now, this is one of those examples where what we're trying to find out is on the bottom of the fraction. So I'm going to do this in two steps. You might prefer to do it in one. If I multiply both sides by x, I get x cos 20 equals 8. And if I divide both sides by cos 20, I get x equals 8 divided by cos 20 degrees. And that is equal to, put it in my calculator, 8 divided by cos 20 degrees, close the brackets, equals 8.51 centimetres. Okay, now it says find the angle JML. So again, I'm just now going to look at the triangle JLM. I'm going to draw it. I'll draw it at its slightly jaunty angle, like that. Now, JL, I've just worked out, so that was X, which was 8.51. This is the angle I want to work out. No, it's not. I need to work out the angle JML. So if that's J, that's M, that's L. JML makes that angle there, which we will call theta, and we'll call, and that is 10 centimetres. Labelling my sides, well, this side is across the triangle from the right angle, so that's the hypotenuse, and this side is opposite theta. Just notice here that in the first triangle, JL was the hypotenuse, but in the second triangle it's the opposite. There's no reason if it's one in one triangle it needs to be the other. It needs to be the same in the other triangle. Not the case. So I've got the opposite and the hypotenuse. So sine theta equals opposite over hypotenuse, because sine SOHCAHTOA, S-O-H, S-O-H. So sine theta, and I don't know what theta is, equals the opposite, 8.51 over 10. Now I'm trying to find the angle here. When I'm trying to find the angle, I want something that turns a ratio into an angle. So that is the inverse sine function. So theta equals sine to the minus 1 8.51 over 10. I do expect to see that written like that in your working. Okay. So, we need to go shift, sign, no, I seem to turn the calculator off. Shift, sign, fraction, 8.51 over 10, close brackets, equals 58.3 degrees. Okay, so side JL is equal to 8.51 centimetres, angle JML, which, as you know, I could write like that, is the same as theta, which is 58.3 degrees. And that's how to do more complicated examples in right-angled triangle trigonometry.